Now, coming to the electron gain enthalpy only, that is, let me tell you here one thing, you just note it down, that in a particular period, that is the elements which have got fully filled or half filled electronic configuration, the outermost subshell, got it? The outermost subshell, if it is fully filled or half filled configuration, then it's considered to be a stable. For example, beryllium, magnesium, got it? It is S subshell is fully filled. Similarly, nitrogen, phosphorus, what you can say, P subshell is half filled. So if an element has got fully filled or half filled configuration, alright, just like noble gases, it is also quite said to be stable in nature. And in that case also, electron gain enthalpy is positive. It is not negative. It is highly positive. Not only positive, I should say highly positive, because it is stable. So hence you can conclude the one which has got stable configuration, alright, you have to overcome the repulsive forces. Alright, due to that particular reason, what you find is that they have got that is positive electron gain enthalpy. So beryllium, magnesium, nitrogen, phosphorus, noble gases, alright, they come under this particular category. Fine. Now next is, if you see in a particular what you can say period, what I said you, that is group 17, or in a particular group I should say, that the group 17 elements have got highest electron gain enthalpy. That is a fluorine, chlorine, bromine, iodine. Alright. So hence I said you also, when you come down the group, electron gain enthalpy decreases, because atomic size increases as well as your screening effect increases. What is we can say. So hence electron gain enthalpy decreases, because it is depends upon this atomic size and the screening effect for that particular purpose. But here is some exception. It's very important. Listen carefully. Now, in case of group 17 elements, what you can say is that chlorine is having high electron gain enthalpy, then fluorine, then bromine, then iodine, we can say that. The electron gain enthalpy of chlorine is more than that of fluorine, then bromine, then iodine. Alright, it's an exception. It should be what? That the fluorine should be more than that of chlorine, but here it is an exception. Alright, chlorine is having more electron gain enthalpy, then fluorine, then bromine and iodine, we can say that. Clear? Why? Let us see the atomic size of fluorine and chlorine. Now, fluorine atomic number is 9. So, 1s2, 2s2, 2p5. Now, you can see it has got two shells. First shell, second shell. See, the principal quantum number, two shells. So, if I draw, that is for fluorine, this is first shell and this is your second shell, let us say. We are having it. First shell 2 electrons, second shell, what you can say, nothing but that is 1, 2, 3, 4, 5, 6, 7 electrons. See, 7 in this way. So this is your fluorine. Now, what about chlorine? Now, chlorine is 17. So 17 means 1s2, 2s2, 2p6, 3s2, 3p5. So it has got 3 shells. Second shell and this is your third shell, we can say that. Fine. So if I draw the structure, it will be first shell, then this is your second shell and this is your third shell, so to say. Alright, 1, 2, here it is 8 electrons is there in the second shell, and the third shell we are having, that is nothing but 7. Now see, both are having 7 electrons in the outermost shell. This also got 7, this also has got 7 electrons. But you see, the fluorine is compact in size compared to that of chlorine. Fluorine is compact and smaller in size compared to that of chlorine. Definitely, because it has got 2 and it has got 3 cells. So definitely the size of the chlorine will be bigger than that of fluorine. So definitely now you tell me that when I add an electron to it, which will readily accept, chlorine or fluorine? Definitely chlorine, because atomic size is bigger. It is going to definitely readily accept compared to fluorine. Alright, it is this particular element is going to readily accept 1 electron because it's bigger. See, atomic size bigger. Here also 7 electrons are there. Here also 7 electrons is there. But you see the size of the outermost shell. Here it's a bigger shell. So definitely space is more. So definitely it is going to readily accept an electron here. In case of chlorine, then fluorine. So hence electron gain enthalpy of chlorine is more than that of fluorine. Fine. Now the question will come readily in your mind. That sir, then bromine also should be greater than that. Iodine still greater? No, we can't compare it. Why? Because chlorine and fluorine, they are gaseous. bromine is a liquid and iodine is a solid. Can we compare a gas to a liquid and a solid? No, they are different states. If you ask me, when we are converting bromine into gaseous state, liquid to gaseous state, isolated gaseous atom, here also same thing will convert into isolated gaseous atom. Got it? So here then also it has to also be converted, na? Because if you are converting this and you are comparing with this, how to compare? This is in the normal state, this is in the excited state. Can you compare? No, because the several questions will come into your mind. That's why we will, okay fine, you have understood that this is gas, this is liquid and solid, so we cannot compare it because they are in three different states of matter, so we can't compare it. But the next question you can ask me, sir, if you are converting this into the gaseous state, okay, how will you convert? By giving energy? That means this will be in the excited state, this will be in which state? Ground state. How will you compare it? It is having more, what you can say, already more energy, it has absorbed energy. It has absorbed energy already. Then only it is getting converted to gaseous state. But that is not the definition of electron gain enthalpy. Got it? That is not the definition of electron gain enthalpy. We can say that. Clear? So in this way, it is not at all comparison. That is that particular thing. So hence electron gain enthalpy of chlorine is greater than that of fluorine. Similarly, in group 16 also sulfur is greater than that of oxygen. We can say that. Clear? Now after that we cannot compare it. Selenium, tellurium, same reason we can say that. Clear? So this is about your electron gain enthalpy. I need to discuss. I have told you about it. The next properties I am going to come is your electronegativity. What is electronegativity? Electronegativity of an element is the tendency of an atom to attract the shared pair of electrons towards itself. Got it? What I said, negativity. Electronegativity denoted by the letter that is chi. This is known as KII. Chi. This symbol is called as chi. We can say that. Electronegativity. It is the tendency of an atom to attract the shared pair of electrons towards itself so as to convert it into a covalent bond, so as to form a covalent bond. Because when it is going to attract the shared pair of electrons towards itself and the sharing is going to take place, then what type of bond is going to form? Definitely covalent bond. So hence electronegativity of an element is a tendency of an atom. Listen carefully, it's a tendency of an atom to attract the shared pair of electrons towards itself. One pair of electrons is going to attract the shared pair of electrons towards itself so as to, what you can say, in a covalent bond, so as to what you can say, convert into a bond formation or a molecule. We can say that. Clear? Fine. Now it is represented with the letter chi. We can say that. Clear? So again I repeat, tendency of an atom to attract the shared pair. Now the question is, when you are moving from left to right, alright, when you are moving from left to right in this way, when you are moving, which element is having a tendency? That is group 1, 2, 3 or group 15, 16, 17. Which element is having a tendency to gain electrons? To attract the shared pair of electrons towards itself? Definitely 15, 16, 17. Because these elements have got high electron gain enthalpy. It is having a tendency to attract the electrons towards itself. Alright, we have already seen just now. Alright, so it does not have, it has got a tendency to rather lose. Alright, it has got low ionization energy. So if it is having low ionization energy means definitely it have a tendency to lose electrons to form a cation. We can say that. So this is having a tendency. Just now we have studied. Alright, so these elements have got a tendency to attract the shared pair of electrons, and moreover what you find is that these are basically non-metals. They are in the liquid and the gaseous state. And non-metals have got a tendency to share electrons to form a covalent bond. You have studied already in the lower classes, somewhere you have studied. So hence, when you move from left to right across a period, electronegativity increases. Same reasons, that is nuclear charge increases. Alright, but when you come down the group, electronegativity decreases. When you are coming down the group, it is decreasing. And when you are going across the period, it is increasing. We can say that. So across the period it increases and down the group it decreases. Alright, why it decreases? Same reason. Because down the group the atomic size increases. Alright, due to the increase in the atomic size, due to the increase in number of shells, electronegativity, what you find is that it decreases. So hence, for that particular reason, remember it. That is, in a periodic table, fluorine is the element which is having the highest electronegativity, that is 4. We can say the value is 4. And cesium, because it is hydrogen, lithium, sodium, potassium, rubidium, cesium. You will say francium? Yeah, francium is a radioactive element. Alright, it's radioactive in nature. So hence its properties is entirely different from that of the other elements. So we don't consider it. So here we are considering the ordinary properties. We consider the periodic properties and the chemical properties, the physical properties. We are comparing that, isn't it? So hence we are not going to consider the francium. We are going to consider cesium only. We consider that. So cesium. So the lowest electronegativity is of that of cesium. It is, I don't remember the value. It is 0 point something. It might be that of the cesium. That is, hope so. The value is 0.7. The cesium, the value is. Alright. So exactly, I don't remember it. It is 0.7 nearly. Alright, and here I remember that is fluorine is nothing but 4. And what I said you here, it does not have any unit. Like in case of electron gain enthalpy, we have seen it is measured in joules or kilocalories or calories. We can say that. Alright, it can also be electron volt. Here we don't have, because what I said you, it's a tendency, and tendency cannot be measured. We can say that we cannot measure the tendency, because I said you the tendency of an atom. So it does not have any unit. First of all, you need to understand it is a pure number. Alright, so hence I wrote it as 4. Hence I wrote it as 0.7. So this particular element, that is fluorine, has got highest electronegativity and cesium has got the lowest electronegativity in a particular group, because down the group decreases and across the period increases. Alright, fine. Now next is, there are different scales. Alright, as we don't have the unit, it is a tendency, so it's very difficult to measure. Alright, it's very difficult to measure. So there are different scales are there. Different scientists have their given different scales. Like we have got the Pauling scale, we have got the Mulliken scale, we have got the Alfred, Rauch scale, we can say that. So the most convincing is your nothing but the Pauling scale, we can say that. We have got the Mulliken scale, we have got the Alfred scale, we have got the Pauling scale. Alright, Pauling, P-A-U-L-I-N-G, the name of the scientist is Pauling. So that is most convincing. Other scales are there, but it has got some other disadvantages. Alright, but the most convincing one, the most promising one, and the most appropriate one, I should say, is the Pauling scale. By the help of Pauling scale, we are not measuring, I should say that, we are just comparing the electronegativity of the element, we can say that, because it's very difficult to measure the electronegativity. I said you, it's just a tendency of an atom. So we can compare it. Alright, we can compare it. So how do we do so? Alright, how do we do so? See, we generally find the electronegativity difference. We generally find. Now, what is that? Suppose there are two elements are there. One is A, another is B. So we will find chi A minus chi B. We can say that. That is electronegativity element A minus electronegativity of element B. What I said you, we find the difference in electronegativity. Why do we find it out? I will tell you. Just now I will tell you why do we find it out. Is equal to 0.10, that is 17 root over of delta. 0.1017 root over of delta. Now what is delta? What does delta stands for? Delta stands for is equal to EAB. Alright. AB is what? It's nothing but, it is nothing but bond length between an atom A and atom B, we can say that. Clear? EAB minus a root over of EAA into EBB. We can say that. Alright? EAA into EBB. Now, what I said, EAA, EBB and EAB. This is what AB, AA, BB, they are the bond length. Bond length between the atom A and B. Bond length between the atom A, bond length between the atom BB. And when I say E means what? Energy. So it is not at the bond dissociation enthalpy. The bond dissociation energy, we can say that. So in this way, this is called as a bond dissociation enthalpy or the bond dissociation energy. Again I repeat, bond dissociation, to break the bond, how much energy is required, that is called as bond dissociation enthalpy or the bond dissociation energy, which is measured in kilojoules per mole. Definitely, energy means it is measured in joules or kilojoules, we can say that, kilojoules per mole of the bonds AB, AA and BB. I said it. Correct? So this is nothing but is your bond dissociation enthalpy or the energy. Again and again I am saying you. So the difference between the two electronegative, what you can say electronegativity, that is chi A minus chi B, is equal to 0.1017 into root over of delta, where delta represents this particular value. All this can be measured. This can all be measured. We can say that. We can measure the bond dissociation enthalpy of the two elements. We can say that. Alright, and the two similar elements, we can measure it. So in this way, this is the most promising one, because we can measure it. Practically we can do it. For that reason I said it is the most appropriate one. So by this, by the Pauling scale, I should say that we can measure the or we can compare the, that is better use the word compare. We can compare the, that is electronegativity of an element. We can say that. Clear? Fine. So in this way we can compare it or measure it, whatever you can say, the electronegativity. And already I said you which element has got the highest electronegativity and which element has got the lowest. Now it depends upon certain factors. So what is the oxidation state of the element? Oxidation. The element which has got the higher oxidation state is considered to be as the highest electronegativity. The element which has got the higher oxidation state. For example, if you are having two elements, two ions, Fe2 plus and Fe3 plus. Fe3 plus has got higher electronegativity than Fe2 plus. Why? Because Fe3 plus, how it is being formed? By the loss of 3 electrons, isn't it? By the loss of 3 electrons, Fe3 plus is being formed. So, and Fe2 plus means by the loss of 2 electrons it is being formed. Isn't it? By the loss of 2 electrons it is being formed. So hence, what you find is that Fe3 plus is having higher electronegativity compared to Fe3 plus, Fe2 plus. Because 3 plus means it is to become neutral. It is going to gain 3 electrons. It is going to gain 3 electrons. So it will be more electronegative. And it is going to gain 2 electrons. It is going to be less electronegative. So higher is the oxidation state. This oxidation state 3 plus, 2 plus, or if you say valency, that also is not wrong, we can say that. But better is to use the word oxidation state, because for the variable valencies we use the word oxidation state. So higher is the oxidation state, higher is its electronegativity. Because more is the oxidation state means more number of electrons it is going to gain. Electrons means electronegativity, because electrons are electronegative in nature. Now, next is nature of the substituents attached to it. Nature of the substituent attached to it. For example, we are having CH3F and we are having CH3I. Now, here what you find is that this is common, CH3 is common. The difference is F and I. Now, which is more electronegative? Fluorine is more electronegative than iodine, we know that. Just now I said it. So, hence, this particular compound is more electronegative than this particular compound. Definitely. Because this is more electronegative than this. So, nature of the substituents which is attached to it. For example, suppose we are having, there is CH4, we are having CH3Cl. Now, you know, here CH4 can also be written as CH3H. We can write, if you want to compare it properly. CH3 common, H and Cl. So, which is more electronegative? When you compare H and Cl, Cl is more electronegative than hydrogen. So, hence, this particular compound is more electronegative than this. We can say that. Clear? In this way. Now, after that, what is the applications of electronegativity? Now, applications of electronegativity is that is from the electronegativity we can know which is metallic and which is non-metallic. The metallic, the substance which are metallic has got less electronegative, means they are more electropositive, because less electronegative means more electropositive, and the substance which are more electronegative are basically non-metals, and the substance which are less electronegative are basically metals. And I said you that when you move from left to right across a period, group 1, 2, 3, 4, these are the, what you can say, groups where you find the metals. So they are less electronegative or more electropositive. And group 15, 16, 17, they are basically the non-metals. Alright, because they are having the higher electronegativity. Just now I said you, we discussed with you. Alright, fluorine is one of the example, I should say that. Clear? Fine. And cesium is another example, I should say that, because it is a metal which is having the lowest electronegativity, we can say that. Similarly, the difference between the polar and the non-polar compounds. Alright, now polar means what? Where there is some difference in electronegativity. That's said to be polar in nature. Where there is some difference in electronegativity. Alright, so these compounds are non-polar in nature. That is H2, O2, N2, Cl2, they are non-polar. Because H2 how it is formed? Between H and H. So these element, whatever the electronegativity, this element is also having the same electron, because both are the same elements. Na? So difference in electronegativity is what? 0. 0 means are we having two poles? Polar means what? There must be two poles. What poles? One positive poles and there is negative poles. How these poles are created? If one of the atom is having tendency to gain, another is having tendency to lose. Got it? So how gain or lose tendency comes? When they are having difference in electronegativity. If one is more electropositive, another is less electropositive. Means if one is electropositive, another is electronegative, then negative is going to lose and the positive is going to gain. Are you following what I am saying? So in this way, what you find is that here both the atoms are similar. Here when both the atoms are similar, that means they are having the same electronegativity. Nobody is going to lose or gain because both they have the same electronegativity. Same thing in case of oxygen also. Both have the same electronegativity. Same thing in case of nitrogen also. Same thing in case of chlorine also. So when you find a homopolar, what you can say molecule, not homopolar, homo molecule. Homo means that is similar, atoms are there. If these similar atoms are there, alright, it is known as a hetero molecule, we can say that. Hetero means dissimilar atoms. So you know that chlorine is negative and H is positive. Listen carefully to this particular thing. So this is said to be polar. Ammonia, this is said to be polar because nitrogen is more electronegative and hydrogen is positive. Water, this is said to be polar because oxygen is negative and hydrogen is positive because two dissimilar elements are there. So when two dissimilar elements are there, then definitely you will find there will be difference in electronegativity. And difference in electronegativity gives rise to what you can say polar character. We can say that. Here there is no difference. If the difference is there, the difference is zero, you can say that. The electronegativity difference is zero. So if the electronegativity difference is zero, then it is a pure covalent bond. It's a pure covalent bond. But if there is some difference in electronegativity, then there is some ionic character. Even if this is a covalent compound, but it has got some ionic character. Alright, so hence, that is Pauling has said that if a particular compound has difference in electronegativity as 1.9, alright, it is said to be polar in nature because it has got 50% covalent character and 50% ionic character. If the difference in electronegativity is 1.9. Now if this difference is increasing, if the difference in electronegativity increases, listen carefully, ionic character increases. Means the ionic character from 50% it becomes 60%, 70%, 80%, 90%, and definitely this is going to decrease. This is going to decrease when it is exactly 1.9. The difference in electronegativity is said to be polar. That polar means what? 50% ionic, 50% covalent. So if the difference is increasing, electronic difference, that is 1.9, after that 1.92, 1.93, 1.96, then 2, then 2.1, if it is increasing, let us say. So as the difference in electronegativity increases more than 1.9, the value increases more than 1.9, so ionic character increases. Increases means from 50% becomes 60, 70 in this way. The reverse is true when the difference in electronegativity decreases. If it is decreasing in this way, it is decreasing. So if it is decreasing, that means what? Ionic character decreases. That means covalent character increases. So this will become, let us say this is your covalent character, this is your ionic character. So covalent character has become 50, then 60, then 70, then 80. Means from 1.9 if it becomes 1.8 or 1.7 or 1.65 or 1.6. So as the difference is going on decreasing and decreasing and decreasing, then covalent character increases. Just now I said, just now you see here what is the difference? It is 0. 0 means it's a pure covalent compound, pure covalent bond here, pure it is. We can say that. Because the difference in electronegativity is exactly 0. So hence that is only I said. When the difference is decreasing and it reaches 0, then it is a pure covalent bond. That is said to be non-polar in nature. So they are non-polar and these are said to be polar in nature. So hence Pauling has given scale that if the difference in electronegativity is exactly 1.9, then it is said to be polar. We can say that. We can say. And if the difference is increasing, electron difference is increasing, then ionic character increasing, means polar character is increasing further. And here if the difference is decreasing, then the polar character is decreasing. That means non-polar character is increasing. And when the difference is becoming almost 0 or nil, then it is said to be pure covalent compound. In this way, on the basis of electronegativity, we can find it out whether it is polar or non-polar, whether it is a pure covalent or it is having ionic character and all these things. Okay, thank you very much.